Oh, okay. Thank you. Um, okay. So Kaya's gonna go back to teaching us our stuff. And I believe we have a Q&A section now, so drop those questions over there. Anything else, put in the regular chat. And yeah, thank you guys for bearing with us.
Okay, guys, we're back. So I found out that these tech issues were caused because the College Board found out we're all gonna get fives. So they rigged it so that they could keep, their pass percentages low. But we're not gonna let that happen because we're all here to get fives. Okay, guys? So we're gonna hop right into it. We just wrapped up with 1.3 elemental composition and the empirical formula. So just remember, if they give you the molecular formula, the most basic one, and then they ask you to change it into the molecular formula, what you're going to do is find the ratio of the molecular formula to the empirical molar masses. And then when you get that ratio, so in this case was 2, you'll multiply the subscript of that empirical formula by that ratio to get the molecular formula. Okay? And now let's keep going. Next thing that's important to know is the composition of mixtures. They don't question this about this too much directly, but it is important to know, as they may refer to it sometimes. So, first thing when you have any kind of matter, you're going to ask if it has a variable composition. So if yes, that means it's a mixture. So variable composition means that like it's made up of different things. Just to clarify that just in case. So if it's yes, if it's made up of different substances, then it's a mixture. And then you're going to ask yourself, is it uniform throughout? So if yes, it's homogeneous, and if no, it's heterogeneous. So some examples of homogeneous mixtures are sweet tea. So, you can't really filter it. It's pretty much just one consistent substance. Versus if you have an ocean with wet sand, obviously then you have two different substance and properties that are mixed together. On the other hand, if it's not a variable composition, then if it's not a variable composition, then it's a pure substance. And then what you're going to ask yourself is if it's a pure substance, is it able to separate into simpler substances? So if it's a pure substance that's able to be broken down even further, then it's a pure compound like H2O. However, if you cannot break it down into a simpler substance, then it's an element, because remember, your elements are pretty much your smallest form of a simple substance. Like you can't break down helium any more than it's already broken down. If you did, that would be something scientifically revolutionary. And next up, reviewing some of the different separation techniques. So remember, on the AP Chem exam, there are some lab technique questions where they may ask you, okay, we have two different substances. They may ask you about the boiling point. They may tell you about the different properties of the substance, and they may ask you how to separate it. So what we're going to do is we're going to go through the different separation techniques that you have to know for the AP Chem exam, because these are the points that you don't have to do any calculations usually for, so you want to make sure you get these points. So first technique is filtering, and filtration is based on the solubility of a substance. The next separation technique is distillation, which is pretty much where you heat it until the two substances separate. And this is based when you have different boiling points. And then the last kind of main separation technique that we focus on is chromatography. And this is based on the polarity of the substance. Now, going into a little bit more about atomic structure, these are your basics. You must know them. Don't let them fool you on these. So our atoms are made of protons, neutrons, and electrons. So protons, what I like to think of, like when I was learning about protons, neutrons, and electrons, what I kind of like to do is like memorize them. Is protons are like sounds like positive, right? P for protons, P for positive. So then you have a +1 charge. And the number of protons is the same as the atomic number. So like all the way on the right, if you take a look, you'll have carbon, the C with a 6 above it. So that's the atomic number. And that's also the number of protons that a atom of carbon has. Next thing you have are your neutrons. So the number of neutrons you have may vary. Sometimes for example, an atom of carbon may have 6 neutrons or it may have 7. But I'm sorry, I think the slide switched. Can we go back? Thanks. So like I was saying, the number of neutrons may vary. Remember, atoms have different isotopes, which is when neutrons vary. But they have no charge. They are kind of like neutral, like it's another similarly to protons. You could think of neutrons as neutral. And these have a charge of 0. They pretty much just kind of function to stabilize the nucleus. As you guys can see on the diagram, you have the protons pretty much like mush with a bunch of different neutrons. And then this helps to stabilize the nucleus. And then finally, you're going to have your electrons, which have a charge of -1. And these are pretty much around the nucleus, and they are considered massless. So if you have 6 electrons or 200 electrons, they won't really impact the mass in AP chemistry. They don't really have a mass of 0, but their mass is negligible. So it is very, 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 very small. So it doesn't even matter, really, for our purposes. And then just remember the general rules. If the number of protons is equal to the number of electrons, then you have a neutral atom. If the number of protons, however, is not equal to the number of electrons, regardless of whether there's more electrons or more protons, then it is an ion because there's a charge, right? So if you have, let's say, 5 protons and 4 electrons, then you're gonna have a positive 1 charge. And remember the different if you have a different number of neutrons for the same number of protons, so like if you have carbon with 7 neutrons or 8 or 6 or however many, remember it's still the same atom, it's just a different isotope, so that means it has a different mass. And just remember the structure of an atom. Remember that the electrons are surrounding the nucleus, and they won't always be in orbitals like these, right? So here you have these nice simple rings, but in reality, electrons exist in an electron cloud, which pretty much means that they're kind of like darting all over the place within a certain area of the nucleus, right? So just remember that may show up in a different way as well in your AP exam. And then something else that to keep in mind with the atomic structure is that the further away the electron, the weaker the attractive force, right? So here we have a lovely little diagram. So we have our nucleus with the smiley face in the center with a more positive charge. And then we have our little electrons circling around it and different energy levels. So the further an electron is from the center, the weaker the force of attraction. And this will come into play later on when it comes to removing an electron from an atom, right? So since it's further away, there's less of an attractive force exerted by the nucleus, right? And there's a formula that helps like illustrate this, the Coulomb force, which is F equals to the constant K, which is equal to Q1 times Q2 over R squared. And the Q pretty much indicates a charge of the charge, and it's the distance between the first and second electron, right? So charge of electron 1, charge of electron 2, and the distance between these two charges. So this will kind of help you determine the kind of force, and you don't need to know this exact formula. You don't have to memorize it. You don't have to worry. This is not another thing you have to memorize, but it kind of just helps to go illustrate that, the further you are from the nucleus, the weaker the force of attraction is. Okay, so that's something really important because it comes into play with a lot of the topics. And then with electron configuration, we also have quantum numbers. So you don't need to know how to assign quantum numbers to electrons for the exam. You just need to understand the broad concept, right? So you have the quantum numbers N, L, ML, and M subscripts S. So just you have to know the allowed values for the different quantum phases. So the allowed values for N are 1, 2, and 3. For L, they're 0, 1, 2, or pretty much N minus 1. For M subscript L, it's for negative L, -1, 0, 1, or positive L. And then for M subscript S, it's positive 1 over 2 or negative 1 over 2. These honestly don't show up too much on the AP exam. So you don't have to stress too much about them because it is a more complex topic. You just need to broadly understand that the quantum numbers influence the orientation and the shape of an orbital and the distance of an electron from a nucleus and the orientation of the electron spin. So that's kind of like what they work for. But this isn't something that's too heavily tested on the AP exam, but you should have like an idea of what it is in a general concept. And then we also have electron configuration, which kind of goes into a little bit with quantum numbers. So you have first thing, you have the Aufbau principle. That's how you pronounce it. And that's kind of a rule that you have to fill the lowest energy orbital first, right? So for example, you have 1s and then you have 2s, right? So 1s is the lower energy orbital, and then you have 2s as the higher energy orbital. You're not going to do 1s and then 2s. You're going to fill the 1s orbital first. So it's kind of like trying to fill a bag with groceries, right? You're not trying to fill each bag with one grocery item and then just going to the next one. You want to make sure one grocery bag is filled first before you go to the next one, unless you want to be carrying like 35 something bags, which is really unnecessary. So that's kind of how I like to think about it. You want to kind of fill up each lowest energy orbital first. So you kind of these orbitals kind of want to be minimalistic. They want to have the least energy orbitals as possible. So the first thing you're going to do is fill the lowest energy orbitals first. Next thing, because of the Pauli exclusion principle, no electrons can have the same set of quantum numbers. So for example, here that's kind of represented by the fact that in the 1s orbital on the right, which is obviously wrong, you'll see the arrows pointing both in the same direction. So they cannot have the same direction. They have to have a opposite spin, which is illustrated by the diagram on the left, which is 1s with arrows pointed in opposite directions, which means that the electrons have opposite spins, which means that they did not have the same quantum numbers. Another thing is Hund's rule. So electrons must fill each empty orbital in the same sublevel before pairing up, right? So what you pretty much want to do is they're kind of like siblings. If anybody has a sibling here, you don't want to share a room with your sibling, right? Like that's like, no, unless you have to. When you have to, then that's different. So that's kind of like Hund's rule. If they have a certain number of sublevels, they want to have their own, right? They only want to pair up if they have to. So like here with the 2p sublevel, you have 2 electrons in the first box with opposite spins, and then you have two other boxes with their own spins, right? So they're not pairing up, even though they could. They want to take their own room. Okay, so kind of like think of it like a little sibling situation. And no, you don't really need to know the names of the rules. It's something that you just have to have like a general idea of, so that if they ask you something regarding this concept, that you have like a decent understanding of it. But they're not going to test it as much as like, let's say, intermolecular forces. But it's something you have to have a general idea. Next thing is the electron configuration. So that's our 1s2, 2s2, 2p6, and so on and so forth. And something that's really good if they ask you for the electron configuration, and this is something that they will ask, like I've seen it on when reviewing previous AP exams, usually you'll have a question on electron configuration, and it's really a matter of just knowing the number of electrons in an atom. So for example, for oxygen, right? You have 1s2, 2s2, 2p6. So oxygen has an atomic number of 8. So that means it has 8 protons. And since oxygen in the sense is a neutral, so it's not an ion in any way, you're going to have 8 electrons as well. So in this case, you'll write 1s2, 2s2, 2p6. Remember that the S sublevel can only have 2 electrons. The P sublevel, you can only have 4 electrons. The D sublevel can only have, so it's 4 for each. So P can only have 6, D can only have 10. F, which they rarely use, sometimes they'll use it, but not often, can only have 14, right? So something to help you kind of know what the maximum sublevel would be is this kind of layout of the periodic table. So you'll see that our alkaline earth metals and alkali metals, they all have a S sublevel. And then if you move onto your your transitional metals, you'll have a VD sublevel. And then pretty much beyond that, you have your P sublevel. And then those odd elements that we almost never use below are the S levels. You may get them, off chance you probably won't, because of the fact that they usually have a very, very high atomic number. But it's just something to be aware of. And then we have the electron configuration, kind of like going over what I said before with electrons' distance and relative strength. Remember, if the electron is further away, it has the nucleus exerts like a lower attractive force. But on the other hand, if the electron is very close to the nucleus, you'll see that it has a stronger force of attraction. So if you're trying to remove an electron that is, let's say, the closest to the nucleus versus one that's further away from the nucleus, the energy required to remove that electron that's very close to the nucleus is going to take significantly more than to remove that electron that's further away from the nucleus. So the further away, the greater the binding energy. And remember, your valence electrons are always, which are the farthest from the nucleus, always have the highest, like they have the most force of attraction exerted on them. And sometimes like they'll ask you, okay, how much like energy do you have to use to remove it? Or like what element is it based on how much energy used to remove it? So usually when you have that big jump in energy change, that means that stops being that it's starting to take one of those electrons that keeps the atom as an octet, which they don't want to do. So now we're going to do a little bit of practice with photoelectron spectroscopy, because they will ask questions like this sometimes. So what is the electron configuration for this neutral element? Okay, so kind of to break down the graph a little bit more before we give you guys the answer. And while you try, I'll explain a little bit about the graph. So the height of the peaks, right? They're not random. They're equal and proportional to the number of electrons, right? And then at the bottom, on the x-axis, you see binding energy. So the closer you go to the left, that's the closer it is to the nucleus. However, if you go more to the right, is the furthest away from the nucleus, right? So you see how the third curve from the right, so pretty much that middle peak, it's, yeah, whoever said in the chat, it is supposed to be 2p6, not 3p6. We were trying to test you on that. Good catch. So it's 1s2, 2s2, 2p6, 3s2, 3p1. So here what you kind of want to do is you'll take into account the total number of electrons, and then seeing where there is the greatest peak, that means that that's the point where the valence electrons are starting to be removed, which is why there's so much more energy required. Because remember, that typically these, atoms, they want to form octets. They're happy in octets. Why? Because they just are. For the AP chemistry exam, that's what you need to know, that they're happy in octets. So when you have that huge peak in like binding energy, it's usually because of like that octet. So now that you guys have like a second to try it, we're going to show you what the electron configuration is. Yeah, so it's pretty much I don't know if it's why it's not popping up on the screen. So it's pretty much 1s2, 2s2, 2p6, 3s2, 3p1, right? So sometimes you can use other elements to kind of abbreviate it, but in this case, it's not really necessary. They don't really do that too much on the AP chemistry exam. They can sometimes, but for usually they won't, because they're not asking you to do like a ridiculously large electron configuration for an element. We can go to the next slide. Yeah, and then again, it's 1s2, 2s2, 3p6, 3s 1s2, 2s2, 2p6, 3s2, 3p1. And then kind of from there, what you do is you add up the total number of electrons. So 2, 2, 6, 2, 1. So that will be 13, right? So that you'll see that it is aluminum. And sometimes what they'll do is they'll do this in kind of like a subscript, right? So they'll take the last noble gas before the element, and then they'll tack on like those last few electrons. If you know how to do this, you can. it's not required for the AP chemistry exam. Some people like to do it as kind of like a shorthand, but I honestly prefer writing it like the normal way, like without the shorthand. But you can do this if you're comfortable with it, or if it's helpful for you, you can, but it's absolutely not necessary. Okay, and now periodic trends, and our other lovely host, Kritika, will take over.
All right, hi guys. Actually, Kaya, could you give me video access? No, all right. Okay, we're just gonna go cameraless for a while. My name is Kritika. I'm another one of the 5able hosts for these cram sessions. I just finished up my first year in college last week. I'm majoring in bio and I have a minor in chem. And I'm super excited to be here reviewing AP Chem with you guys. AP Chem was really exciting. So we're gonna talk about periodic trends. So this is answering someone's question from earlier. So for the first thing we're going to talk about is effective nuclear charge, which is also written as ZF as, okay, 1 second. All right, so it's also written as ZF. I know some people pronounce it as ZEF, but this means the actual force that electrons feel from the nucleus. So when we're talking about the force electrons feel from the nucleus, we know that the nucleus is positively charged because of the protons there, and the electrons obviously are negatively charged, so they do have an attractive force between them. And this is referring to the attractive force within one molecule itself. So when you're moving across a row, the number of protons increases while the energy shell stays the same. So all in one row, all electrons will be a similar distance from the nucleus. So we are increasing positive charge without changing the distance. So the effective nuclear charge actually increases. When we're moving down a column, we're still increasing the number of protons. However, we're adding another energy shell. So all the electrons in a different column will be further, in the lower column will be further away from the nucleus. So the nucleus isn't able to exert as much of a positive charge on these farther away electrons. So the effective nuclear charge is weaker when you go down a column. And this relates back to Coulomb's law. I know someone in the chat was saying that Coulomb's law explains like everything in chemistry. So if you look back at Coulomb's law, it's not, oh, sorry. If you look at Coulomb's law, then you can tell that distance has more of an impact on the actual attraction than charge. We can go to the next slide. So next we have ionization energy. So this is the energy needed to remove a valence electron from the molecule. It has the same pattern as effective nuclear charge. So the greater the effective nuclear charge, the greater the ionization energy. Because if you have a greater effective nuclear charge, that means the force that, once again, the force that the nucleus is exerting on the electron is strong. So it's holding the electron strongly, it's attracting it strongly in place closer to it. So it's going to require more energy to actually remove that valence electron. So it increases as you move towards the right and as you move up the periodic table. Real chemist named their son Zeph. I love that. Okay, so electronegativity is a really important concept in chemistry. So this is how strongly a nucleus attracts electrons of another atom. So it's really similar to effective nuclear charge, but the main difference between effective nuclear charge and electronegativity is that electronegativity is how strongly one nucleus of one atom attracts the electrons of another atom, while effective nuclear charge is within the same molecule. So, could you go back? Thank you. So this increases as you move from left to right, and it also increases as you move from down to up in the periodic table. A good way that I like to remember it, really handy, is knowing that the most electronegative atom, the most electronegative element is fluorine. So the farther you move from it, the less electronegative you are, and the closer you are to fluorine, the more electronegative you likely will be. Next, we have electron affinity, which isn't really as important as the first few ones that we've gone over, but it is good to know. So electron affinity is the amount of energy released when an electron is added to an atom in the gaseous state. So as the effective nuclear charge increases, we're also going to have a higher electron affinity. So once again, like the other three that we just went over, it has the same pattern where it increases from left to right and increases as you move up the electron, the periodic table. Okay, next slide. Next, we have atomic and ionic radii. I know a lot of teachers in the AP test love to talk about this. So the radii is the distance between the nucleus and the valence electrons. So the greater the effective nuclear charge is, that means we're going to have a smaller radius, because once again, the nucleus is going to exert a stronger force on the electrons and bring it closer to it. So if we have an anion, which is a negative, that means we have an extra electron compared to the neutral state of whatever element. We're going to have an extra electron, but we're going to have the same amount of protons. So we're going to have more of a negative charge than what we had before. So since we don't increase the protons, we have the same positive charge as before. So it's not really going to attract all the electrons as tight as before or tighter. It's going to be less of an attractive force. So therefore the ionic radii of an anion is going to be bigger than its neutral state. And then for the cation, the opposite is true. So cation is going to be when an ion is positively charged. That means it has one less electron. So we have the same nucleus as when it's in the neutral state, same positive charge. And when we have the cation, we're going to have less electrons for the nucleus to attract. So it's able to attract a stronger force on each of the electrons, therefore bringing the radius down. So this is just a summary of the 4 trends that we just went over. I would recommend screenshotting this, keeping it in your notes. These are going to be really important for a lot of questions on the AP exam. We can just do a quick review. So ionization energy, electron affinity, and electronegativity all follow the same trend. They follow the same trend as the effective nuclear charge. So it increases as you move from left to right and from down to up. And then atomic and ionic radius moves the opposite way. Okay, so now we're going to talk about the reactivity of metals. So alkali and alkaline earth metals, which are the first 2 groups that you see all the way on the left, they really readily lose electrons because they only have 1 or 2 valence electrons. So they're really eager to lose those to kind of get rid of them. And that's the easiest way to reach the octet, which, if you guys don't know, that's when an atom has 8 valence electrons. Whereas this transition metals, which are in yellow here on the periodic table, these are more stable and less reactive compared to the alkali and alkaline earth metals. Right, now we're going to talk about the reactivity of nonmetals. So that's going to be everything on the right side. Sorry, I think I might have said right for the metals. Those are on the left side. The right side is the nonmetals. So the examples that they want us to look at are carbon and fluorine. So C, it's over there in blue, and F is over there in purple. So C has 4 valence electrons, whereas F has 7 valence electrons. So we know the octet rule. We know that 7 valence electrons is so close to 8 valence electrons. So it's going to want to get an extra electron more than the carbon, because if the carbon gets 1 extra electron, it's still not going to fulfill the octet. So the F will really want that valence electron. So it will be really reactive. We see this with all halogens, which is that group 7. So everything there in that purple color, they're really reactive, and they usually get electrons to fulfill the octet. If we look at something like neon, which is in gray on the second period, this has 8 electrons, so it already has a full octet. So it's not going to be really reactive because it doesn't really need to. And this applies to all of those, all the elements on that column, which are called the noble gases. Okay, now we're going to talk about valence electrons and ionic compounds. So when forming ions, elements typically gain or lose the minimum number of electrons necessary to achieve a full octet. So we just talked about an octet. So this is when there are 8 electrons, 8 valence electrons. So all the elements really want to reach this octet state because that's when they're the most stable. So when you lose electrons, that is when you form a cation. And when you gain electrons, that's when you form an ion. So a way that I like to remember this is when you lose electrons, you'll be positive. So cats have paws, so that's something silly I use. And for when you gain electrons, you gain more negative, so you gain a negative charge. So that is an anion, and the easiest way that I use for this is AN, A negative. I did mu positive with PAW, yes. All right. So ionic bonds are formed when electrons, electrons are transferred, and this is an ionic compound. So for example, in this picture over to the right, we have Na and Cl. So Na has the blue electrons and Cl has the orange electrons. So we can see that Na actually transferred one of its electrons over to the Cl. So if it didn't transfer to the Cl, then it would have an extra shell with just one lone valence electron, and Cl would have the 7 in its outer shell, only missing 1. So if Na is able to transfer one sole valence electron to Cl, both of them will be happy, both of them will be stable and have their octet fulfilled. So we're going to look at the configuration, the electron configuration down at the bottom. So this is what I was talking about before. This is the configuration on the left of Na before transferring its proton. So you can see that it has electron. So you can see it has one electron in the s orbital, in the shell, and then Cl, it has 5 instead of 6. So once the electron transfer does happen, Na is left with 2p6 and 2s2, and Cl is left with 3s2 and 3p6. All right, we're going to take a really quick break. You guys have done a lot of chemistry so far, and I think your brains need a break.
Hey guys, so we're back from our little break, and the first thing we're gonna do is we're gonna take a little practice quiz. So, to see what we retained from our unit 1 and to see if there's anything we need to go over. So, scan the QR code.
Wait, I thought we weren't doing the practice quiz. It's already 8:30. I need to get to 2 more units.
Okay, got it. Then we'll move over.
Yeah, okay.
We won't do the practice quizzes, guys. Sorry, no samosa yet. But next time we'll have samosa, okay? Next time samosa. Don't worry, guys. We'll make up for it. We'll make up for it. But we'll link samosa music so you guys can, listen to it like therapeutically. But we'll move on. And remember, practice questions are available on the 5 cram session page. So, Unit 2, Molecular and Ionic Compound Structures and Properties. So some of the topics in Unit 2, because there's quite a bit to get through, so just to give you a brief overview, we have the different types of chemical bonds, intermolecular forces and molecular stability, the structure of ionic compounds, the structure of metals and alloys, Lewis diagrams, resonance and formal charge, VSEPR, and bond hybridization. So these are some of this we went over during the previews if any of you watched them. But we're going to go over them again now in more depth, so you guys know everything they have to do about Unit 2. So the types of chemical bonds. So this is very, very important because you could get a lot of different questions asking you about chemical bonding, right? In a lot of combined with a lot of different units. So you have to know this. Even though it may seem simple, these fundamentals really are what end up biting you in the butt if you don't know them. So make sure you know your chemical bonds like the back of your hand. So first thing, we have covalent bonds. So in covalent bonds, you have electrons being shared, and this is only between a non-metal and another non-metal, right? And in this cases, atoms have similar electronegativity, which is what allows these electrons to be equally shared. What I like to think of covalent is covalent is co, so like next to each other. So that's kind of like, if you kind of warp it in your mind, it kind of makes you think of sharing it. So that's what I like to do with covalent. The next kind of bonding is ionic bonds. And in ionic bonding, you have electrons transferred. And this happens between non-metals and metals. And that's because of the very, very large difference in electronegativity between metals and non-metals. So as we know, non-metals, for example, are halogens, have like much more desire to have take electrons, so fill that octet, versus metals, they're kind of like, okay, you could take an electron or two, right? Depending on the amount of valence electrons they have, they won't be as as a high electronegativity, because for metals, giving away electrons will give them that octet faster than trying to take electrons, right? So in this case, ionic, these are where you get your ions from when electrons are transferred. And then lastly, we have metallic bonds. And these ones you won't see as often as covalent or ionic bonds, but they still do come up. They still are important. And this is when electrons are shared, kind of similarly to covalent bonds, except that it's in between metals and metals, and the valence electrons are delocalized, right? So you won't really draw like a Lewis diagram of a covalent electrons you won't draw it a Lewis structure like you will with a covalent bond, right? You'll kind of have these electrons that are delocalized, so they exist more like a cloud around the nucleus. And then with electronegativity, you typically follow like that diagonal upwards, like you see. So with francium being the least electronegative, while fluorine is the most electronegative, right? So you have it increasing upwards as you go up a group and across a period, right? And then it'll be kind of go up on like a diagonal as well. So, and just kind of just to give you like a professional definition of electronegativity, is the ability of an atom to attract electrons, which is determined pretty much by how many electrons an atom needs to form that octet that they desire, right? And determines the bond type based on the different type of atoms that are bonding together. And like I said before, the octet is what atoms really want. They want those 8 valence electrons to be happy. And then the higher electronegativity between the two atoms they have present, right? So let's say we take potassium and chlorine, right? So we have KCl. So it's gonna be like a tug of war between them to get that electron, right? And it'll go to fluorine because it's more electronegative. It wants to fill that octet more than, let's say, potassium. Another really important concept is nonpolar versus polar covalent bonds. So atomic relationships, kind of like as a joke, are pretty much basically just atoms doing whatever they can to become stable, right? So they don't care if they steal your electrons or anything like that. They just want to become stable. And then, so now we have nonpolar and polar covalent bonds, right? So in nonpolar covalent bonds, you have valence electrons that are being shared between atoms of similar electronegativity to make a nonpolar covalent bond, right? And then with polar covalent bonds, you have atoms with higher electronegativity develop a partial negative charge. And in single bonds, there's a greater difference in electronegativity, which leads to greater bond dipoles. So in nonpolar, you pretty much have like these very nice atoms that they're willing to like share a little bit more. But in polar covalent bonds, then they're like, no, this is mine. Like they're pulling it away, which leads you to have like those partial positive and partial negative charge, which leads to greater bond dipoles. Yeah, and then we're gonna move on. The slide's frozen. Oops, looks like the College Board's trying to stop us again, guys.
Yeah, I can share it real quick.
And while the sides are being pulled up, the next thing after nonpolar and polar covalent bonds is the structure, right, of the nonpolar and polar molecules. So in a second, we'll pull up the slides so you guys can see for yourself. And essentially, with nonpolar molecules, you have symmetrical structures, right? So with nonpolar molecules, you have symmetrical structures, which means pretty much that everything lines up. So if you were like to split it in half, it's the same on both sides, right? Oh my God, this is the most music. So, like I was saying, the nonpolar molecules are symmetrical, and the polar molecules like H2O are non-symmetrical. So if you imagine the Lewis structure for H2O in your head, you'll kind of see that hydrogen is like up here in the middle, and then you have the oxygens on either side, right? So it's not symmetrical. It's not evenly split like something like PO4, for example, which will be like the phosphorus will be in the center and the oxygens will be on all four sides, right? So that's different. And it doesn't have to be on all four sides. For example, if you have Cl2, that's also a nonpolar situation because it's like evenly split, right? So you have those positive, you don't have like that drastic partially positive and partially negative charge. Yeah. And then here we kind of see more examples. So you'll have the Cl4, right? So you see how it's all of them are surrounding Ci4, where all of the chlorines are surrounding the iodine, and it's surrounding it like evenly, right? So it's not just three, it's not it's even on both sides, right? Can you guys see the slides good now? Okay, perfect. Okay, so like I was saying, nonpolar are symmetrical, right? So you kind of just have to like, that's something you more or less have to remember. If anybody has any good mnemonics for nonpolar or any little tricks to remember it, feel free to drop them in the chat. Sometimes what I like to think what my brain kind of like remembers it is when I think of polar, I think of magnet, right? So a magnet has partial charges, positive and negative. So for example, with the water, we have a partial positive and partial negative charge. So when I hear polar, I think of magnet. And when I think of non-polar, I think of not magnet, which means that there is no positive partial charges, positive or negative. It cancels out evenly, right? So it's just pretty much not not positive or negative charged anything. So that's kind of what I like to think of when it's polar or non-polar. Ooh, I like that. Snap. Symmetrical, non-polar, asymmetrical, polar. That's a good one, guys. I'm writing that down. So we have snap. That's another good one. So symmetrical is non-polar. Asymmetrical is polar. Okay? And then we'll go on to the next slide. So intermolecular forces are super duper 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 important. If you guys look at like the AP chemistry breakdown, you may say like, oh, unit 3, it's, unit 3, not that important. But fun fact, did you know that unit 3 makes up 18 to 22% of your AP Chem test? So you got to know your intermolecular forces. So know your intermolecular forces. Don't panic. They're not that hard. We'll help you remember them today. And you can get plenty of practice if available. So you have, well, we're doing the intermolecular forces first. We have to address those. So intermolecular forces are between two atoms, and they're pretty much what hold atoms together in a molecule, right? So before you even address the HCl, that is a liquid that's together, you have to address what's holding the H and the Cl together. So the type of intramolecular forces from weakest to strongest are nonpolar covalent bonds because they're sharing electrons. Polar covalent bonds, they also share electrons. You have the ionic bonds, and these either form a cation or an anion. It forms a cation and an ion, I should say, because the electrons are transferred. So one of them becomes more positively charged, and the other one becomes more negatively charged. And then you have the metallic bonds, which are the delocalized electrons, like we set up earlier. So in terms of potential energy and stability relative to these intramolecular forces, the lower the potential energy, the more stable it is. And the more bonds, and the shorter, which means that they are shorter bonds, means that there's more potential energy. So kind of to like remember this, if you think of like for the lower potential energy, if something has like less energy, or if you're heating something, right, and if you're heating like a liquid and you're changing it to a gas, that gas is not in the form that's as stable as a liquid, or let's say a solid, right? You won't ever be asked to find bond length specifically. They may ask you how many bonds exist, and that you find by drawing a Lewis structure. And we'll go more into that, drawing Lewis structures later. So one thing we will do with bonds, right? We won't be measuring bond length, right? But we will compare bond energies, right? So the more bonds that you have present, the more that like the strength increases, right? So if you, for example, if you have a carbon single bonded to a carbon, or really just any atom bonded to another atom, if you have a single bond, you will have the least energy compared to if you have a triple bond, right? So as the number of bonds increases, the stronger that bonding is. And another thing to remember is that if you have more bonding, the length of those bonds becomes shorter, okay? So if you have one bond, right, it may keep the atoms at a distance like this, but if you have 3 bonds, it's stronger and it's shorter. So that's kind of like the strength of it, kind of pulling it together more. And as you go down a group, the distances between the valence electrons and nucleus increase, and the attractive forces and electronegativity decrease. So as potential energy decreases, you need less energy to break these bonds. And then a lot of times they'll give you a graph like this, the potential energy versus distance between atoms, right? So you have the potential energy curve on your right, and they'll ask you different things, right? So at a larger distance, right? So if you have a larger distance on this curve, it's more attractive forces, versus if you have a shorter distance, you'll have more repulsive forces. That's because the electrons of one atom interacts with electrons of another atom, right? So if the atoms are super, super close together, right? But they're both have like those negative, the negative charges because of the, the electrons. If they're super close to each other, they're going to repel, right? Because like charges repel. So those electrons in the outer shells of that atom will want to repel each other. Versus if they're really, really far apart, they're going to feel more attractive forces, right? So the kind of the point of this potential energy curve is to find like that little balance point between that repulsive and attractive force, right? So that's what pretty much happens with this curve. And as you have that little dip at the bottom is kind of like that ideal sweet spot where they tend to kind of finally form that bond because it's not too repulsive and it's not too attractive. Okay. And just remember, the stronger bond the bond is, the shorter the bond length. And the stronger the bond is, usually it may have like more than one. If it's like the forces of the bonding forces between this and this atom are this much, you'll usually have like, and it's like a high number, you can be like more of those bonds that are existing. And then the equilibrium bond length is, like I said, the distance between atoms that hold the least potential energy. And this is the most stable. So that point all the way at the bottom, right before it swoops back up, right, where they have the dashed line going through the middle, that's the equilibrium bond length. That's where the ideal bond length wants to be, so that the atoms are not being too attractive and they're not being too repulsive. So we're going to do a little practice question really quickly. A potential energy diagram for chlorine 2 is shown in the following graph. Based on the graph, what is the bond length in picometers for Cl2? Okay. So if you look here on this graph, right, you'll see that little bottom peak that I told you about, like the little swoop before it goes back up, is around 200. So that bond length in picometers for Cl2 will be about 200s. All right. And then a student finds that the average AlCl bond length is 220 picometers, and the average bond energy is 425 kilojoules per mole. Draw the potential energy curve for the average AlCl bond on the preceding graph. So pretty much what you would do is draw a very, very similar graph, except that bottom peak will line up with 220. So like now we'll see the answers, right? So you see it's a similar graph, except it adjusts because of the average bond energy, which shifts it more downwards. But that bottom peak is still around the value where x is equal to 220, like seen in the previous question. And now we're going to get into Coulomb's law. So Coulomb's law pretty much reminds you that the magnitude, the magnitude of charge, the greater the charge, the stronger the equals the stronger attraction. And the Coulomb's law is usually applied to ionic bonds, and it helps measure the attraction between these two atoms. And remember that the interaction strength is proportional to the charge on each atom. And the larger charge leads to stronger interactions. For example, with higher melting point, if you have a higher ion charge, right? So if it's like a +3 versus like a +1, the higher the ion charge, so that +3 will need more energy for the bond to break.
All right, I'm back. I'm gonna take over for a bit from Kaya, and I'm going to talk about some Lewis structures. I know this is everyone's very favorite topic. It's one of my favorites, actually. So we use valence structures to represent the valence electrons, Lewis structures to represent the valence electrons around an atom. And they also act as a template for more complex concepts. So basically what you take away from that is that you should be really comfortable with these. And even beyond AP chemistry, for example, in organic chemistry, you are using Lewis structures all the time. So their total valence electrons are derived from the periodic table. So if you take a look at the periodic table, based on the column number that it is, or the group number that your element is in, that is how many valence electrons will be there, if you're not going to give a number to the transition metals. And so one of these dots is equal to 1 electron on the Lewis structures. So 2 of them would mean 1 electron pair. And Lewis structures also have lines. So 1 line means 1 electron pair. So the lines are typically drawn between two different atoms. So it symbolizes a shared electron pair. So when you count up the number of lines and the number of dot pairs, that's how many, or dots, that's how many total valence electrons that are around a certain atom. And once again, these lines you would count as sort of as two electrons because they're shared, they're from one from each of the atoms that the bond is between, and they're shared between the two. And not incorporating shape just yet, Lewis structures are not representative of the 3D structures. They're just a building block, but they are able to tell us a lot about the actual molecule and about the reactions it undergoes. So we're going to do some practice. We are at 8:45 right now, so I'm just going to walk through it. So the first thing you do when you draw the Lewis structure, I would recommend writing the tips down, the steps down. First, you identify the central atom. So we're practicing with O2. So in this case, this is a diatomic molecule. So there's not really a central atom, but a lot of the times carbon, especially if you're dealing with like an organic compound, obviously, carbon will be the central atom. Next, you determine the number of valence electrons. So once again, this is based off the periodic table. Oxygen is group 6, which means it has 6 valence electrons. And O2 is just 2 oxygens. So you multiply the number of valence electrons in one oxygen by 2. So in O2, the diatomic molecule, you will have 12 valence electrons. Next, you determine the number of electron pairs. So we have 12 valence electrons. So if you just divide that by 2, we'll end up with 6 electron pairs total. Then we're going to draw the skeleton with single bonds. So we just have the 2 O's and a single bond between them. So this bond, once again, it represents 2 electrons, so 1 electron pair. So we, out of the 6 electron pairs that we have available, we used one of them. We have 5 of them left. Next, we place the electron pairs, which would be like the dots. So we are going to place 2 on top of each oxygen. So that leaves us with 1, 2. Can you guys see my pointer? If you can, I'm pointing at the lone pairs on top of the oxygen. So if we just count the lone pairs, 1, 2, 3, 4 lone pairs on each oxygen. And then we're going to have the bond between the 2 oxygens. So each oxygen has 1, 2, 3, 4, 5, 6 electrons on it right now. So we've used 5 of the valence electron pairs already, and we have 1 left. So with that, what we're going to do is try to fill the octet by drawing in a double bond, by drawing in the pi bond. So we use all 6 of them, and if you check, both of the oxygens have fulfilled the octet rule. So once again, the 1 oxygen has 4 valence, 4 lone pairs. So that's 4, and then it's sharing 4 with the other oxygen. And you want to verify the octet rule, which is what we just did. 4 valence electrons, 2 bonds will mean 4 electrons plus 4 electrons equals 8 electrons per oxygen. We have some more practice. We'll just quickly walk through those again. So NH4, so this is a little bit different than the O2. So in the O2, there was no charge on the O2, on the molecule, right? But NH4 does have a charge on it. So what does that mean? We know that charges have to do with the number of electrons that the molecules either has excess or is lacking. So since it's positive, we know that we have 1 less negative electron. So we have 5 electrons from the N, from the nitrogen, which is in group 5, and then we have 4 hydrogens, which are group 1, so 4 electrons coming from the different hydrogens, and we add those up, we get 9. However, because we do account for the 1 missing electron, that means we have 8 valence electrons, and that leaves us with 4 electron pairs. So following the steps outlined before, they drew the skeleton in, and then they added the lone pairs here on nitrogen to fulfill the octet. Nitrogen, as you can see, has 1, 2, 3, 4, 5, 6, 7, 8 electrons. So yeah, 2 pairs from the 2 bonds and 2 pairs from the lone pairs. Next, we have our next molecule, and from the P, we're going to have 5 valence electrons, and from the O, we're going to have 6 twice, because we have 2 molecules, 2 atoms of oxygen, and we're just going to do the same thing. I'm just going to go over it really quick because we've already done this twice. So we have a negative charge on this one, which means we have 3 extra electrons. So we're going to add that to however many that we would have gotten from just the atoms. So 5 plus 2 times 6 plus 3 equals 20 electrons. So we're left with 10 electron pairs. And this is one of the molecules that they came up with. So now we're going to move on to resonance structures. This one is not as important for AP Chem. I think they introduced it to you in AP Chem as being more important in organic chemistry, but it is pretty important to know. So the main question that resonance structures address is, what if the molecule can be drawn in more than one way? Welcome to resonance structures. So, I think, can you guys see there? I think it should be working. So all lone pairs and bonds can be distributed in different ways. So the way that we see a molecule drawn on the paper with all its electrons in certain positions isn't how it's always going to be in real life. Because once again, the electrons are always moving around the molecule, so they can end up in different places. In resonance structures, helps us consolidate the different places that these electrons can be and represent it more accurately to real life. So all structures can exist, but the molecule will structure itself in a way to ensure the smallest formal charge. So resonance, in reality, the structure is an average of all possible Lewis structures that we just went over. So if you look at the bottom, here we have one molecule to the left and another to the right, directly to the right in the middle. So we can see that the double bond moved from being above, the electrons in the double bond moved from being right above the carbon to being right to the right of the carbon. And this is possible because once again, the electrons are able to be localized all over the molecule. And what we have underlined in orange is called a resonance hybrid. So the resonance hybrid is kind of a combination of both of the resonance structures that we just saw on the left. And these dotted lines mean that the double bond can be in both places. It's kind of an average of the two double bond locations. So formal charge, we just talked about it, but we didn't really define it. So formal charge is really helpful when we're determining the most efficient resonance structure. So this is how we calculate formal charge, and it is, I would write this down as well. It's the number of valence shell electrons minus the number of lone pair electrons minus 1/2 of the number of bonding electrons. And we calculate formal charge for each individual atom in a molecule. So the way that I actually like to think about it, I consider it a shortcut because it just makes the formal charge equation a little less confusing with the 1/2, is I count the number of valence shell electrons, or find it from the periodic table, how many valence electrons should be around that one atom. So for example, we have an example here actually. So for oxygen, it's group 6 on the periodic table, which means it should have 6 valence electrons. So 6 is the number we start off with, minus lone pair electrons. So minus 1, 2, 3, 4 lone pairs. So 6 minus 4, we're at 2 right now. And then instead of, you could either do 1/2 number of bonding electrons. So that's, we have a double bond right here, which is 4 electrons being shared between the carbon and oxygen. So 1/2 of 4 is 2. So 2 minus 2 is 0. But the way I think about it is just the number of lines that you see. So 2 minus 2 lines is 0. So when we're looking at what we have on the bottom, so these are all different resonance structures of carbon dioxide, CO2. So we can either have it like it is all the way on the left, with carbon having 2 double bonds and the oxygen being the center and oxygen having 4 lone pairs each. Or we can have it as carbon having a triple bond to one of the oxygens and a single bond to the other. Or even as an oxygen being the central atom, double bonded to the carbon and also being double bonded to another oxygen. So based on an analysis of the formal charges, we can tell that the structure all the way to the left is going to be the most stable because it has the least formal charges. We also want to look out for the least number of formal charges, not just when you add them up together, because Obviously, when you add +1 and -1 together, you'll get 0. Same thing for these two. We're looking for the least number of formal charges. Okay. Now we're going to go on to VSEPR and bond hybridization. I know this was something that was really confusing when I took AP Chem, and it isn't really all that important, but once again, just another good thing to know. Okay. So the VSEPR theory is what we use to predict molecular shapes based on valence shell electron pair repulsion theory. That was a handful. That's why we call it VSEPR. So the main point of VSEPR is this valence shell electron repulsion. So knowing that valence shell electrons do repulse each other, and that's what helps us determine what shape a molecule could be. So there is a limitation to the VSEPR, which is that VSEPR doesn't really give us information about bond lengths or the presence of multiple bonds. So it's not going to be 100% accurate, but for our purposes, it is pretty accurate for the molecules that we'll be looking at. You also have to determine polarity using electronegativity to determine the relative charge of atoms in a molecule, which Kaya went over earlier, and we do have a couple more practice examples of that. So some reminders with VSEPR. So on the right here, you're going to see a chart with different shapes, different VSEPR molecules, and some examples of them. When studying this, I wouldn't make flashcards. I would make flashcards, but we are kind of getting close to the AP exam. So a good way to study this would be just looking at the chart, trying to cover some spots up, and then seeing if you're able to recognize the shape. So yeah, do a lot of practice and become familiar with some patterns that you are able to observe. For example, when determining shape, you treat lone pairs as a bond. However, lone pairs are stronger at repelling. They repel more than bonded electrons. So bond angle will be slightly shorter. So let's see, a good example of this would be in H2O. So H2O is basically an oxygen here. Pretend my head is the oxygen, and I'm going to have two hydrogens coming out of me here. So hydrogen and hydrogen. However, to get the octet, so these are just 2 electrons each, but to get the octet, I do need 4 more lone pairs. So imagine they're just like on top of my head. So even though I only have like 2 actual atoms sticking out of me, they're not going to go straight across because the electrons here will repulse the other electrons on the hydrogen. So with that repulsion, I probably look really silly right now, but it's for you guys. The repulsion is going to shift these bonds over here. So the bond angle between my 2 hydrogens will be smaller. It does require some memorization, but instead of just looking at the chart and just memorizing everything, do some practice. So this is a chart of some molecular shapes. I think this one is a better representation than the other chart. That one was a little confusing. The study tip that they suggested is if you were given this table with only the first row and column, could you fill out the entire table? Okay, so if you guys want to screenshot this, I'll leave it up for another couple seconds and then move on. All right. So here we're going to have some examples of VSEPR. So this structure is a linear structure, and the bond angle, you guys can put in the chat if you know. We can all play a little guessing game. If not, 180. Okay, yeah, perfect. 180. Okay, what about tetrahedral? Okay, it's not exactly a consensus, but it is 109.5. Okay, what about trigonal planar? Pyramidal, sorry. Okay, and yeah. So it's going to be actually 107. And it's smaller than the 109.5 because this yellow that you have right there, that is going to be a lone pair. So it's going to push the electrons, the bonds a bit closer to each other. What about linear? 180, yep. And trigonal planar? 120. And angled. Okay. less than 120. All right. Okay, we're going to do here. I'm going to put both of the practices up for like a minute, and then we're just going to go over the answer. So for VSEPR, it says draw and explain the difference between a molecule of H2O and a molecule of CO2. Include bond angles in the names of molecular shapes. Polarity practice, using your drawing of H2O, label the partial charge and overall charge. And is a molecule polar or non-polar? And then do the same for CO2. I'm just going to go ahead and review the answers since we are running a bit short on time. So H2O has a bent shape, and just have the angle degrees. Yeah, it's going to be less than 120 degrees, and CO2 will be linear with an angle of 180 degrees. Okay. And the reason for the difference, even though both molecules have 3 atoms, is because H2O does have the lone pairs, as you guys remember, they were on my head, while CO2 doesn't have that. And then for polarity practice, this is what the H2O looks like, and this is what CO2 looks like. So H2O is polar. There's a difference in polarity, but one second. CO2 is actually non-polar. Even though there is a difference in polarity between the carbon and oxygen, these two, the poles that are formed from them actually cancel each other out. So then we consider it non-polar. They are symmetric. So now we're going to talk about hybridization. So hybridization is how atomic orbitals mix to form new hybrid orbitals during the formation of covalent bonds. And this helps us predict molecular shapes, bond angles, and it can also tell us more about reactivity. So something that I like to do for hybridization, it is fairly straightforward, but a little shortcut that I have is when you look at a molecule, for example, the one on the right, top right, there's a little black dot, and then there are the 2 things attached to it. That's why it's 180 degrees. So it has 2 things attached to it. So 1, 2, SP, so 2 letters. And if you look at the one below, we're going to have a molecule, an atom with 1, 2, 3 other atoms attached to it. So we're going to have 3 letters. So SP, and then it says SP2. So we're going to count the 2 a second time. So SPP, SP2. So that's just a shortcut that I'd like to do with it. All right. And this is for the last part of VSEPR. So we're going to talk about bond order, which is the number of bonding pairs of electrons between 2 atoms. So for example, all of these have different bond orders. Can you guys put what you think the first bond order is for just the C with a single bond to this other C? So the first one has a bond order of 1, the second one has a bond order of 2, and the third one has a bond order of 3. So it's kind of just like how many lines are there. Okay, measure of polarity is what dipole presence is. Dipole presence is to measure polarity, and it's used when there's unequal distribution of electrons in a bond or in a molecule, and the electrons will end up moving towards the more electronegative atom. So if you look at this arrow, the arrowhead, like the little triangle thing, is pointed towards the more electronegative atom, and the little dash in the arrow is pointed towards the less the more the one with a partial negative positive charge. So dipole moments do have a magnitude and direction, and these are really important when you're assessing whether a molecule is polar or non-polar based on symmetry, to see whether or not the dipoles cancel each other out. Sometimes dipoles can be stronger than other ones, so that's also something really important to keep in mind. Okay, checkpoint. There are 3 proposed Lewis diagrams for ALCL shown below, and there are some questions. We're just going to go over them really quick. So it's saying that the AlCl3 molecule has a trigonal planar geometry. Which diagram 1, 2, or 3 can be eliminated based on just geometry? Use the VSEPR theory. And then for number 2, it says, which of the 3 diagrams is the best representation for bonding in AlCl3? And then you justify using formal charge. So for the first question, diagram 2 is not, what was it? Is not trigonal planar because it is actually trigonal pyramidal, which you can tell by the fact that it has an extra pair of an extra lone pair on the Al. And for diagram 2, all atoms in diagram 1 have a formal charge of 0, so therefore it is the best representation. Okay. We have a break coming up. I think we will cut it a bit short because we do still have a lot of content to go over. But here, how about we do 3 minutes? All right, so you guys can use this time to stretch, get some water, and you can also ask questions in the chat. Me and the other host will be here to answer. And this review is going to run until 10, but we might have to run over for a little bit because we did have technical difficulties at the beginning.
Hey guys, okay, we're back from the break. No samosa time. We're gonna skip the practice questions because, like we said, we're a little bit short on time. We were supposed to end at 9:30, but we still have a chunk of material to get through. So we're gonna get through this. So, like I was mentioning earlier, intermolecular forces, 18 to 22% of the exam. So big portion. Make sure you understand it. So, quick overview. We're going to go over the different types of intermolecular forces, the properties of solids, liquids, and gases, ideal gas law, KMT, or kinetic molecular theory, and the deviation from ideal gas laws. We also have solutions and mixtures, representations of solutions, a separation of mixture, solubility, spectroscopy and EM spectrum, photoelectric effect, and Beer-Lambert law. So it's a pretty heavy set, but we're gonna get through all of it. So first thing, intermolecular forces, not to be confused with the intramolecular forces. Inter is between two molecules. Like how when you think of an interstate, interstate kind of is like highways between two states, right? So same concept with intermolecular forces. These are the forces between two molecules. And then if you have intra, the prefix indicates that's inside the molecule. So don't confuse them. Also, intermolecular forces are much, much weaker than intramolecular forces, okay? They're so very, very important. It's easier to separate the intermolecular forces between two water molecules versus the H to separate the H and O atom inside of the molecule itself. Yeah. So kind of going through the different London intermolecular forces, you have your London dispersion forces, and these are between all molecules, okay? If they ever ask you what is the force of it like that exists, and your mind literally goes blank and you don't remember nonpolar, polar, what's going on? London dispersion forces is always guaranteed to be an answer, okay? London dispersion forces exist between all molecules, but they are also the weakest type of intermolecular force. The second force that we have are dipole forces, okay? And these exist only between polar molecules, okay? And after this, we have hydrogen bonding. And hydrogen bonding isn't actually a bond. So this is kind of a misnomer, right? But this intermolecular force is called a hydrogen bond. And it's really just hydrogen bonded to nitrogen, oxygen, or fluorine, right? And these bonds are a stronger version of dipole forces. And they are usually like they're abnormally strong, okay? And then we have ion dipole forces, and these exist between an ion and a polar molecule, and they're the strongest one by far. So, like I said before, if they ever ask you what is present in all molecules, London dispersion forces, okay? But remember that these are also the weakest ones, and that's because London dispersion forces exist because of temporarily induced dipoles. So like you see in this little diagram in the center, you have like these blue blobs, and these pretty much represent your different molecules, right? So as your electrons move around that electron cloud, at some point you have a more positive charge on one side because let's say all the electrons went here, and that made this part more positively charged. And let's say then here you have another molecule, and all of the other electrons on a consequence went here. So now you have a partial positive and a partial negative charge, right? So now they have that temporary attraction. So that's why that's how London dispersion forces come about, and they're temporary, right? Like the electrons don't always stay rooted there. And the strength of London dispersion forces consequently increases with increasing size and the increased number of electrons because it allows them to be more polarizable, okay? And then the second thing, dipoles only exist if there's a polar molecule, right? So kind of going back to London dispersion forces only exist between non-polar molecules, okay? So if you ever think of putting dipole-dipole down as a choice, if in a multiple choice or in a free response, know that dipole-dipole and all the other forces cannot exist in nonpolar molecules. Nonpolar molecules only have London dispersion forces. And now going back to dipole-dipole forces, these dipole-dipole forces are permanent dipoles in polar molecules. And they kind of like, they stay there. They're not because of the polarizability of the molecule. And the strength of dipole-dipoles increases with increasing electronegativity difference. So the greater difference in electronegativity there is, the stronger the dipole-dipole force. And this creates a partial charge, and it's closer to the closer it is to full charge, the stronger the attractive force is. And like I said earlier, hydrogen bonding is a special type of dipole-dipole, and it exists between hydrogen and nitrogen, oxygen, or fluorine. And there's a very, very, very big electronegativity difference, which makes it have a much stronger attraction. Now, to kind of move on to ion dipole forces, ion dipole forces, kind of as the name suggests, are between ions and a polar molecule. Remember, if there's anything you take away from the section, non-polar molecules only have London dispersion forces as an intermolecular force. Never, never, ever, ever put like a dipole-dipole force between a non-polar molecule if non-polar molecules only have London dispersion forces. Okay? So ion dipole forces, similar to dipole-dipole forces, have permanent dipoles, and they have full charges in ions, which makes them stronger than dipole-dipole forces, right? And the strength of these increases similarly with increasing electronegativity difference and greater magnitude of charge. So kind of to try to identify which intermolecular forces are present, first, you're going to try to ask yourself, are polar molecules involved? If polar molecules are not involved, what are we saying? Drop it in the chat really quickly. Yes, London dispersion forces. Nothing else, okay? London dispersion forces. Okay, but what if polar molecules are involved? Then we ask ourselves, are ions involved? And if ions are involved, then what do we have? Ion dipole, guys, okay? Ion dipole. But remember, it's kind of like the name suggests. If you have a polar molecule and you have an ion, just know you have to have that ion dipole, okay? It's always going to be an ion dipole. But if ions are not involved, then it would be yes, dipole-dipole. And then you also want to consider if it's bonded to if hydrogen is bonded to nitrogen, oxygen, or fluorine, to kind of see if you have that special type of dipole-dipole bonding, which is dipole-dipole force, which is hydrogen bonding. Okay? So that's really good to remember. And remember, LDFs are your weakest, ion dipoles are your strongest, in that order. So this is a great graph, a chart. So later on, you can go to your own slides and screenshot that. And now we're going to walk through a really quickly with this FRQ for AP Chem. So since we are running out a little bit of time, so answer the following questions related to HBr and HF. In the following table, list all the types of intermolecular forces present in pure samples of HBr and HF. And then part B asks to find the enthalpy of vaporization, heat of vaporization for each liquid. It's provided in the following table. Based on the types and relative strengths of intermolecular forces, explain why delta H of HF is greater than that of HBr. Okay, so kind of to break that down a little bit, when it asks you to list the intermolecular forces for HBr and for HF, the first thing we're going to put down is London dispersion forces, because they exist between all molecules, okay? So that was the first. Then the next thing for HBr, since HBr is a polar molecule, we're going to have dipole-dipole attractions, okay? And the same thing will exist for HF, except with HF, we have the presence of hydrogen and fluorine, which means that there is hydrogen bonding also involved. Okay. For the exam, it'd be better to write out London dispersion forces rather than use an abbreviation, just not to risk getting points taken off. And then for the second part of this question, for the enthalpy of vaporization, the heat of vaporization is greater, the enthalpy of vaporization is greater for H of F than HBr because the overall intermolecular forces in H of F are stronger than those in HBr due to the fact that hydrogen bonding exists. And like we know, hydrogen bonding is one of the stronger types of IMFs. So due to the hydrogen bonding present in HF, the more energy is required to separate molecules in that HF. The next thing we're going to go over is properties of solids. So, the different types of solids that you're going to get are covalent network solids, and these solids are pretty much atoms that are held together by a covalent bond network, and like I said, the forces are covalent bonds. And the properties of covalent network solids are high melting points and boiling points, high solubility, and good conductivity. What I like to do to help remember these properties is I like to remember one of like the examples provided, right? So like if you take a diamond, for instance, if you take a diamond or carbon and you think about its properties, it has a very high melting point or boiling point. I assume if you would try to melt a diamond on a stove top, it would not melt. So therefore high melting point, boiling point. You have high solubility and you have great conductivity, right? And then for molecular solids, you have atoms and molecules that are held with intermolecular forces, like hydrogen bonding, dipole-dipole forces, and then dispersion forces. And the properties of these molecular solids are low melting point and boiling point. They're not very soluble, and they have quite a poor conductivity. And some examples are H2O and CO2. For ionic solids, you have cations and anions, and these forces are held up together for by electrostatic attractions. And the properties of these are high melting point and boiling point. They're hard and brittle, and they have generally poor conductivity. And some examples of this are Ki, MgOH, salts in general, and NaCl. And then some properties of metallic solids are they're atoms held together by metallic bonds. And the properties of these are that they have varying melting points and hardnesses. So even since they're varying, they're not as likely to ask you about the melting point or hardness of these molecules. But they do know that they're varying. But they generally have a high conductivity and they're very malleable. If you would think of a metal, you know that they're conductive. I mean, we have metals like copper or iron in our chargers, which allows our phones to charge. And similarly, they're very malleable. So back again to that charger example, you have chargers, you know, they're very flexible with the different metals that they have inside them. So they're malleable. And then we have our solids, liquids, and gases, right? So our solids, liquids, and gases range in intermolecular force strength. So among solids, you have the strongest intermolecular force strength since it requires the most strength to kind of keep it together, right? Like it's hard to separate a solid versus a gas, which is already like not even held together at that point, really. So solids are your strongest intermolecular forces, while gases are your weakest intermolecular forces. And solids are usually also your most dense like phase versus gases are your least dense, and liquids are always somewhat in the middle. With fluidity, solids are the least fluid, while gases are the most fluid, which kind of means like they're not really that rigid. And then with compressibility, you have like close to no compressibility with solids. Similarly with liquids, you really don't have too much compressibility, but with gases, you have some good compressibility. You have most of them are compressible. And then we have our ideal gas law. So with ideal gas laws, you have to know these few different symbols. So the R is your ideal gas constant, which is 8.314 joules per mole inverse Kelvin inverse. And you have to choose the right units, right? Because there's different units for your gas constant R. So depending on the problem, whether you're dealing with moles, atoms, torrs, different things like that, you have to choose the right units for the gas constant. Second thing, you have your P for pressure, V for volume, T for temperature in Kelvin. Remember temperature in Kelvin unless they ask you otherwise. And then you have your N, which is moles. Torrs is just a unit of pressure. So just like atmosphere. And the ideal gas law is PV equals nRT. So pretty much the ideal gas law is like, okay, but what if I change this? And what if I change that? What will happen to these? So starting off, what if I kept the number of moles and the temperature constant? And in this case, and then you could also ask yourself, what if I want to change in the system from, what if I want to compare change in the system from 1 to 2? And this is known as Boyle's law, right? So you have compared, you can compare the moles, and if you keep the moles and temperature constant, what you pretty much are left with are N, R, and T being constants, and you kind of call that K, and that will give you PV equals K, and then you have P equals K over V, and you have that kind of indirect relationship. Versus if you want to compare two systems, you have P1 V1 equals K, and P2 V2 equals K. And then that K equals K, so P1 and V2 is equal to P2 V2. And this can make finding any variables, they can make any variables constant and find the resulting relationship. So it's all these mini laws can really just be derived from PV equals nRT. Yeah. So that's where they all come from. So with Boyle's law, you kind of have these cases where as pressure increases, volume increases, they're indirectly proportional. And in this case, you take the PV equals nRT formula, and you kind of have N and T as constants. Remember, we're not going to put R as a constant because R is always a constant, right? On the AP Chemistry reference table, you'll see R as a constant. So in cases where you're finding these different gas laws, just know R is always a constant. With Charles's law, you have temperature increasing with volume, and that kind of gives you the relationship of V over 1 over T over 1 equals V2 over T2. And that's a directly proportional relationship. And in that case, the moles and the pressure are constant. For Gay-Lussac's law, you have temperature increase as pressure increases, and that means P1 over T1 equals P2 over T2. And this is again a directly proportional relationship. In this case, the number of moles and volume are constant. And then finally, Avogadro's law. As number of moles increases, the volume increases as well. And this makes V1 over N1 equal to V2 over N2. So this is another directly proportional relationship. So just something to keep in mind. Boyle's law is the only one that's indirectly proportional. And you don't have to remember any of these like relationships like explicitly. As long as you know your overall like gas law, like PV equals nRT, you can always modify it to find any of these relationships. So now we're going to get into the ideal gas law. So we have Dalton's law of partial pressure. So pretty much what this means is the pressure of a particular gas in relation to the total pressure is directly proportional to the number of moles of a particular gas in a relationship to the total number of moles within a closed container, right? So kind of to go over what these different variables are in our equation in our formula that we have. P sub A is the pressure in atmosphere of a particular gas. So gas A could be the, CO2 gas, or really any kind of gas. And then P subtotal is the total pressure within a closed container. Then you have X sub A, which is the mole fraction of a particular gas. And total moles is the total number of moles that are present within a closed container. So in this case, you have P of A, which is the pressure of a particular gas, is equal to the total pressure times the mole fraction of that particular gas. And you find the mole fraction of a particular gas by writing the moles of A over the total moles, right? And then to find the total pressure, what you would do in any case is you would add the sum of the different pressures present in a certain container system. So now we're going to run through a quick FRQ. So HCl is a molecular gas as a pure substance, but acts as an acid and aqueous solution. A sample of HCl is stored in a rigid 6-liter container at 745 atm and 296 Kelvin. Calculate the number of moles of HCl in the container. And then 2, the rigid 6-liter container of HCl is cooled to a temperature of 271 Kelvin. Calculate the new pressure in atm of the HCl. Right? So for the first part, what you're going to use is that equation, PV equals nRT. And what you're going to do is you're kind of going to manipulate it a little bit, right? So the question asks for number of moles of HCl. So you would rearrange the equation so it's set to equal to N, and then you plug in the different values that they gave you. And from that, you get 1.84 moles. For the second part of the question, they ask you to calculate the new pressure. And with that, similarly, you use the PV equals nRT, and you pretty much drop all the constants to get P1 over T1 is equal to P2 over T2. And then once you modify that slightly to make it equal to P2, you'll plug in the values that they gave you again, and you should get 6.82 atmosphere. And then in this situation, of course, there's more than one way. You could use the P1 over T1, or you could use the PV equals nRT. So we're gonna cut to the next section. Kritika will take over as we are going a little bit over time, and we want to make sure that we give you guys all the information. And just in case you guys want to get more practice in, remember that the 5-able cram questions are available.
Hey guys, taking over again. As Kaya said, we're just going to be skipping the breaks and the FRQs, but you will have access to the slideshow and this recording after. So I would recommend going back in, and the questions that we picked are really good. So I just recommend doing them on your own and checking them with the answer key. So we're going to go over the kinetic molecular theory now. So there are 5 parts of it. So number 1 is motion. Gases are in constant random motion. Volume. Gases are super tiny, so they have negligible volume. 3, gases do not attract or repel, so they have negligible forces. 4, energy. No energy is lost in collisions. There's constant kinetic energy. And 5, kinetic energy and temperature. So at the same temperature, all gases have the same average kinetic energy. So that's temperature, yes. So these are assumptions that we base the ideal gas off of. Yes. So now we're going to talk about the Maxwell-Boltzmann distribution. So it goes into kinetic energy. So for a given atom or molecule, if you increase the temperature, the average kinetic energy will increase because the molecules move faster in a warmer environment. So that means that if you have a colder environment, for example, where the temperature is 100 Kelvin, a higher fraction of molecules will be moving slower. Whereas if you increase the temperature to something like 1000 Kelvin, then you'll have a greater fraction of molecules moving at a faster velocity. For example, if you look at the 100K versus 1000K, if you look under those curves, in the 100K curve, there is not a single molecule moving more than 1000 meters per second. Whereas if you look at the 1000 Kelvin curve, you have almost half of them moving at 1000 meters per second or greater. Also, for any given temperature, if you decrease the size of an atom, of a molecule, it will have an increased average kinetic energy. Smaller atoms and molecules are able to move quicker. Okay. So we also do have to take into account some deviations from the ideal gas law. So at low temperatures, we have to recognize that average kinetic energy decreases because gas molecules move slower. So if gas molecules are moving slower and they're not colliding all the time, then that will give it more time to interact with each other and have forces that are bonding them closer together. So this is an example that's illustrating it. See, in the left hand, you just have them moving around, whereas on the right hand, you have them forming attractions and more IMFs. At high pressure, gases no longer have negligible volume relative to their surroundings. So at a low pressure, the volume of gas is negligible, whereas in the high pressure, the volume gets significant. So we're just going to skip over this FRQ. Once again, you will have access to the slides, so you can come back and redo these questions. The kinetic molecular theory is pretty important to know, so I would highly recommend looking back at these. Okay, now we have solutions in mixtures. So a mixture is when two or more materials that are not chemically bonded are mixed together, and they can either be homogeneous or heterogeneous. So as you can see, a homogeneous mixture on the left-hand side, you're not really going to be able to tell that it is a mixture. You're not going to be able to see individual particles. Whereas if you look at a heterogeneous mixture, or heterogeneous mixture, you're going to be able to kind of differentiate between more distinct particles. So in this picture, you can see how there's a separation between the water in the sand and the heterogeneous mixture. Whereas in the bottom, you can't really tell a difference between the water and sugar in the mixture. They kind of blend together to be one, like to be uniform throughout the whole volume. So solutions are homogeneous mixtures only. And they are, once again, as I said, uniform in composition. So a solute is the particle or substance that is being dissolved in some solvents. And the solvent is the substance that does the dissolving. And together, these things are the solution. Solubility is a measure of how well the solute can actually be dissolved in the solvent. So there's some factors that affect solubility. So if we increase the temperature, we're basically letting the molecules in the solution move faster. And if they move faster, they have a higher chance of running into each other and reacting, or which in this case would be dissolving. So increasing the temperature increases the solubility of solids. If you increase the temperature, you will end up decreasing the solubility of gases. So it's the opposite for solids and gases. If you increase the pressure of gases, you're actually going to increase solubility. An increase in pressure usually comes with a decrease in volume. So if there's less, a smaller volume where the gases are interacting, then they're more likely dissolve. Next, we have more about solutions and mixtures. So we're going to talk about concentration. So molarity is a measure. It tells us how many moles of solute are dissolved per 1 liter of solution. It's always going to be moles per liter. And in dilutions, the number of moles of the solute stays the same, but the volume of the solution does change. So we're going to have a really handy formula for this. M1V1 equals M2V2, where M1 is the number of moles in the first solution before you dilute it. And then same thing for V1, this is volume before dilution. And then M2 and V2 are the moles and volume after dilution. So that, keep in mind that capital M is molarity, not the number of moles. Because the number of moles won't change throughout. However, the molarity, so the measured concentration will. So for example, in this diagram on the right, we have a concentration of 20 molarities. So 8 moles over 0.4 liters. However, we're going to add 0.9 more liters, and this will give us, here I have to do the math. So this will give us a new volume. So we have 1.3 and, oh, sorry, it's going to be 0.9 instead as a volume. So this will give us a new molarity. M1V2 is a pretty useful formula for the AP exam, and also for, I think, almost anything where you're dealing with solutions. So ways to represent solutions, representations of solutions. So 2 important things to know is a strong electrolyte versus a weak electrolyte. So a strong electrolyte is something that completely dissociates in water. So this will be things like strong acids and bases. Make sure that you memorize those. And ionic compounds, and they will also be able to conduct electricity. Weak electrolytes, on the other hand, only partially dissociate in water, unlike strong electrolytes, and these will be things like weak acids and bases. So for memorizing strong acids and weak acids, I would recommend memorizing the strong acids and weak acids, strong acids and strong bases. And once you have the list of those, basically anything else will be a weaker acid or base. So it's asking us to draw a particular model of these two molecules. So for the first one, this is a stronger electrolyte, so it will be completely dissociated, whereas HF, it's a weaker acid. So it's only going to be partially dissociated. You see how on the upper left corner, we have the fluorine and the hydrogen being dissociated. However, in all other molecules, they are connected. Okay, now Kaya is going to come in and talk about separation of solutions.
Hey guys, I'm hopping back in now, and we're gonna go over distillation. All right, so this is the first way you can separate solutions. And kind of the way this works, if we could go to the next slide. Yep. So you're pretty much separating a liquid mixture based on a boiling point. And this kind of, we touched upon it earlier. But what essentially happens is the mixture is heated until the more volatile component evaporates, right? So that's the more volatile component is the one with the lower boiling point. So if they have very different boiling points, then you're usually going to use distillation, right, to separate them. So pretty much what happens is the condensing tools cools the vapor and turns it back into liquid, which makes the separate component collected into a receiving flask to separate from the mixture. So like you see on the side, in part 1, you see it's being heated. Then in part 2, you kind of see that it's being condensed, that vapor that was just heated. And then in part 3, that mixture is being set back into another flask, which separates it. Second off, when separating solutions, we have chromatography. And this separates liquid mixtures based on polarity, right? So you'll notice that all these different separation methods, they're based on different properties. So the last one was with different boiling points, and this has to do with polarity, with how polar it is. So what you'll pretty much do is you spot your mixture to the bottom of a chromatography paper, and then you immerse the bottom of the paper in a small amount of solvent. So for example, water. And then you allow the solvent to run upwards through capillary action. And depending on how far these like dots will travel, it kind of tells you about the different like polarity of the mixtures, and it kind of helps you like separate them as well. You don't have to go too in depth into them, but you should be aware of the different types and what they're used for in case it comes up on an AP Chem exam. And pretty much the rectangle is the chromatography paper. Like I said, the gray is solvent as you dip it through. The green, yellow, and red are the components of the mixture. And in general, with these chromatography papers, the farther the dot travels, the more polar it is. So the more soluble it is in a polar solvent, right? So like here, the green one is on travel the furthest, is the most polar, most soluble in a polar solvent. Because remember, like dissolves like, so if it's polar, and if it's in a polar solvent, then it's also the most soluble. Next thing we have is solubility. And some factors affecting solubility are temperature and pressure. Increased temperature will make it increase solubility for most solid solutes, and increased temperature will decrease solubility for all gas solutes. Okay, and then increasing pressure will increase solubility for all gas solutes. So remember, it varies a little bit depending on whether there is whether it is a gas or a solid solute. For polarity, like I mentioned earlier, like dissolves like. So for example, polar solutes will dissolve much better in polar solvents, and similarly with nonpolar solutes and nonpolar solvents, the same applies. So remember, just like dissolves like. Next thing with concentration is as you increase the concentration of a solvent, you increase the solubility, right? Because the more solvents are in a molecule, the more chances of interaction with each molecule, with each solute, sorry. And then we have surface area. And surface area also affects improved solubility because the smaller and the more less chunky like the solute particles are, the greater surface area they have. For example, if I have a tablet versus a powder, right? The powder is able to cover more surface area than that solid rigid tablet. And this greater surface area allows it to be more exposure to solvent. And then other substances, so adding other substances to a solution may react with the existing ions, and may involve it to like compete for solvent interaction, etc. And this was more determined on a case basis, whether it improves solubility or decreases solubility. Next up, we have spectroscopy and the electromagnetic spectrum. So with spectroscopy, it's the use of electromagnetic radiation to study the properties of atoms and molecules, right? So two key formulas you have here are energy is equal to H, which is Planck's constant, times V, which is the frequency. And then you have the speed of light is equal to wavelength times frequency. And pretty much you don't have to know and memorize the exact graphs that'll show up. You should be familiar with them. But high frequency is a shorter wavelength as you have more cycles, right, in a shorter amount of time. And lower frequency has a longer wavelength because there's less cycles per a certain amount of time, right? And all this information is pretty much on the AP reference sheet. So you don't have to worry about remembering it. One thing that may be important to remember is the different types of rays, right? So you have from radio rays to gamma rays. And sometimes they'll ask you, oh, we want to see the bonds between molecules. What kind of rays will we use, right? And this is kind of where it's important to know these different types. So you have radio waves, microwaves, infrared, visible, ultraviolet, X-ray, and gamma rays. Gamma rays are your strongest, and they allow you to see the more microscopic particles like atomic nuclei, right, which are really, really, really small. X-rays allow you to see atoms, ultraviolet rays allow you to see molecules, visible rays allow you to see different bacteria, infrared, you can see like a pinpoint. Microwave, they won't ask as much about microwaves or radio waves, and you don't have to worry too much about those. They may sometimes ask you like, oh, we're trying to see bonds between these two molecules. What will we use to determine the number of bonds? And then you will have to like specify, oh, maybe it's ultraviolet or it's this or it's that. But my radio waves and microwaves, you kind of think about it like logically. You can like you use a microwave and things like that. So like I personally, to remember it, I associate it with like a common item. So I assume that it's like, oh, it's not too, it can't see things that are way too small. Versus gamma rays are pretty known to be very strong. And similarly with X-rays, people always run out of the room when you're doing an X-ray. So you know that those are stronger and therefore you can see smaller particles. Another thing that's kind of important is the photoelectric effect, right? And this is pretty much what happens when light rays strike a metal. And what happens is that when these light rays strike metal, you have electrons that are like ejected from the metal, right? So, and this gave evidence to the fact that light behaves as a wave and a particle. This is not as crucial for AP chemistry. It's a good thing to know if you're in physics. And you should be aware of it for chemistry too, but it's not something that you have to hammer in. And just know that a light particle is a photon. And with energy, it like collides with electrons on a metal surface, right? So the light collides with the metals, and that like the electrons on the surface, it kind of collides with that. And the energy is transferred to the electron, causing so since the energy is transferred to the electron, the electrons have enough energy to be ejective. And notice how photons' energy is quantized. Just like pay attention to that as well. Another important law in chemistry is Beer-Lambert law. So you have A, which stands for absorbance. This E symbol is molar absorptivity, and B is path length, and C is concentration. So what you'll use to kind of determine this is a spectrophometer, right? So pretty much you have to just like know like if for like an experimental consideration, you have to know the sides have to be cleaned with a cuvette. The sides of the cuvette have to be clean, and the sides of the cuvette have to be rinsed with a solution, kind of to ensure that clarity. And pretty much as you pass an incident light through the cuvette, and then you kind of have like that transmitted light, and pretty much you have B, which is the path length or the kind of like the width of the cuvette. And this helps you determine the molar absorbivity as well as like the concentration and other things like that. And this formula is given on the AP exam. Usually they'll tell you that the absorbivity is, they'll give you the value for the absorbivity or for any of the other variables, and you'll be able to solve like that. You won't actually have to be able to like analyze, you won't have to analyze a cuvette or anything like that. And we're gonna skip over this again, for the sake of time, because we've gone over for half an hour. And then I think we're going to skip through this so that we can do the cram quiz at the end. Or I mean, sorry guys, I messed up. So now we're going to have Tika take over for the practice quiz. Or I'm maybe she's having some difficulties. So if you guys could go ahead, scan the QR code to go to the practice quiz. Let's set this up. Or I think Josh is going to take over. Yep. So everybody get ready for the samosas. And we're going to do just a few questions. Yeah.
Hey guys, can you hear me? Yeah. My camera doesn't seem to be working. You cannot, Anuva, you cannot start your video because the host has stopped it? Is that, can you give me access to that?
Try now.
Okay. No, it still doesn't let me. Oh, wait. Anyway. Oh, okay, let me start screen sharing then. Right. Can you guys all see the cram quiz? Yep, okay, great. Once we have about like 100 people, we can get started, or we'll get started at 9:56, whichever one comes first. The screen share isn't centered. Is it good now? I'm not sure what that means. Okay, that's good. I think you can change that by adjusting. There's like a slider. If you go and hover on the border of the thing, you can change it. Yeah. All right, I'll get started now. You guys can't hear the music? I can hear the music. I don't know why you guys cannot hear the music.
Are you sharing your
Peace.
screen? Try only sharing a tab.
I'm on like Zoom, the app. Let me edit my screen share. Can I change the settings of my screen share? Like share. Like, you guys hear now?
Oh, there we go. Yeah, we can hear it now.
Okay. Alright. Which property is characteristic of metals that can be attributed primarily to CF electron theory? Seems like most of you got this right. It is electrical conductivity because, as you know, the electrons are just kind of really moving around in the CF electrons theory, which allows the metal to be conductive. Maxwell. No, thank you. Are those AP Chem questions? They are not AP Chem questions, but they're good reviews. Seems like you guys did good on this one too. Covalent network solids, remember that's like your diamond, your silicon dioxide. It's just a huge network of covalent bonds holding everything together. Yep. Electrostatic forces, A, is referring to ionic compounds. And another commonly selected answer is D, weak intermolecular forces. That's referring to like molecular covalent compounds. Covalent solids don't have ions. That is correct. That's correct, yeah. These are more like content questions. Seems like you guys did mostly good on this too. Graphite is a network covalent solid, just like the previous question was referring to. And the rest are A, C, and D are all ionic compounds. Wait, they've all been B. That's a coincidence. right, so this one was a little bit more tricky for us. So this is a common thing they'll ask. Solid that can conduct electricity in the molten state, but not in the solid state. That always refers to an ionic solid. In an ionic solid, remember, in the solid state, it is very organized. The atoms are not able to move. The individual ions are not able to move. But when you melt it down to this molten state, these individual ions are able to move, and therefore they are able to conduct electricity. Covalent network solids, it depends on the solid, but if you melt them, they're not going to conduct electricity either. Molecular solids, if you melt water, it's suddenly not going to conduct electricity, and a metallic solid conducts electricity in the solid state. Okay, I don't know what just happened. So yeah, Pascal is a very commonly used unit of pressure. It's derived from the SI units. Mole, obviously, you guys know, is not about pressure. Joule is a unit of energy, and watt is joule per second. So neither of those are pressure. Remember, pressure is force over area. ATM is also a commonly used unit of pressure. So is bar, so is torr, so is millimeter mercury. There are tons of units of pressure. $100,000 pascals are equal to 1 bar, which is roughly 1 ATM. All right, so this is your P1 times V1 equals your P2 times V2. If you have V2 as V1 divided by 2, that means P2 would have to be P2 would have to equal 2 times P1. So that's it. They're indirectly related. Exactly. Actually a song, but I've never heard of this song. All right, this isn't really a question they'll ask you on the AP exam, but it's good to know just in case. Oh, it's a real song, Carnival in Bahia. That's cool. Yeah, it's Charles as well. Gay-Lussac's is pressure and temperature. Henry's law is, I think, volume and temperature, if I'm not mistaken. And Avogadro's law is moles and volume. should be increases. I'm not sure what's wrong with the question. All right, let's just pretend that the question didn't happen. Next question. That question, the previous question was wrong. It happened. Sorry about that. Let's just pretend it right. If the volume of the gas increases, the number of moles has to increase. If you hold all other factors constant. That question didn't specify whether you hold all other factors constant. Yeah, that's Avogadro as well. Doesn't sometimes the reaction shift? So there's no reaction going on yet. We haven't gotten to the point in AP Chem where reactions can occur. That's tomorrow and the day after. All right, you guys are pretty good with this one. The volume doubles. Again, volume and temperature are directly proportional. So if temperature doubles, volume doubles as well. All right, so after the next question, we will be ending the quiz to just go over our Q&A for the night, and then we'll be wrapping up the stream afterwards. So this is our second to last question. Yeah, so one of the assumptions of kinetic molecular theory is that all the collisions between particles are elastic. So that means like they collide and they bounce perfectly off each other. Formally, that just means that the kinetic energy is conserved in every collision. You can just imagine as if it bounces perfectly off each other without impacting one another too much. This is our last question, guys. I don't think you need to know the real gas law. I'm assuming you're referring to the van der Waals equation, but it is helpful to know how things can deviate from ideality, because I think that is a situation that they can ask in the exam. All right, so last question. You guys did really good on this one. As you know, when temperatures are low, intermolecular attractions can play a stronger effect because you're moving around less. So those intermolecular attractions can have a greater impact on molecular path, and that means a greater impact on all the other properties of the gas. I think we're done with the quiz for tonight. Let me end this stream. Yep. I think now is Q&A time.
We are running a little bit late, just because it's 9:10, and I know we had a lot of technical difficulties. So, we have a little bit of, we have the survey. I just put it in the chat. There's a link, and just like put any feedback if you want to see more of something. I promise you guys will do more practice next session, which is tomorrow, and we'll be doing units 4 and 5. Kinetics, my favorite unit. But we'll see you guys tomorrow, and we'll make sure to have a lot of time for the Q&A. Fingers crossed that College Board does not try to sabotage us again. So, yeah. Anyways, thank you guys so much for joining us tonight. I hope you guys learned a lot within the 3 hours we spent together, and thank you guys so much for being patient once again for our technical difficulties. We'll plan to use Crowdcast tomorrow, and if not, then we'll be joining you guys back on Zoom. So just look out on that. So anyways, thank you guys so much for joining. And we'll see you guys tomorrow. Bye everyone. And then I will see the hosts on the huddle.